Hello and welcome back to another YouTube video. Today we are going to be discussing the adiabatic flame temperature. So we're going to start off by looking at a system here. And this system is going to be a closed system. And in this closed system we have some material going in, and this material is made up of air and fuel. And what we have coming out of this system is a flame. And this flame is really just hot gas. So we know that air is made up of 79% nitrogen and also 21% oxygen. And that'll come in important in our stoichiometry later. And then the fuels we're going to be using today are methane, ethane, and propane. So we've got CH4, C2H6, C3H8. And these are our fuels. And so what we're going to go ahead and do is do an energy balance. But before we do that and go through and write out the whole long equation, we can notice a few things that will allow us to simplify the equation quite a bit. We know that this is an adiabatic system. And what that tells us is that the heat, there's no heat going, no heat being lost, and no additional heat going into this situation. It also tells us that there is no potential energy and no kinetic energy. And then because this problem is at steady state, we know that there is no mass change in the system. And what this allows us to say is that the enthalpy going in is equal to the enthalpy going out. Because this is such a simplified situation, we have such a simplified form of the energy balance. And what we want to know is about the heat of formation and the energies, because those energies will allow us to determine the temperature of the flame. And I guess it would be important to say that the temperature going in, we're going to start off at a temperature of 298 kelvins, and then our goal is to find the temperature going out. So we don't know what this is. We're just going to call that T. So we're trying to find the temperature of this flame. And we're going to do that using the heat of formations. So we know that the heat of formation temperature T is equal to the heat of formation at temperature, the initial temperature, 298 kelvins, plus, and normally we would have a regular specific heat, just CP, but in this case, because we're dealing with temperatures that are closer to an extreme range, just more outside of our ideal conditions, we need to integrate this specific heat with respect to the temperature, and we want to do that from our starting temperature to our final temperature. And so I'm sure you noticed immediately I had this ChemCAD equation 107 up here. And what this is this integration, or is this specific heat. It's an equation for the specific heat. And so what we're going to need to do is go in and calculate the specific heat with an integral. I don't want to do that integral. Doesn't look like a lot of fun. So we're going to go ahead and pull over our friend Wolfram Alpha to do it for us. So the main important parts, we can do the integral of A. That I can do in my head. So we're going to go ahead and do the hyperbolic integrals in Wolfram Alpha. So I'm going to pull that over here. So we've got the integral of this part here, right here, and it comes out to C times the hyperbolic cotangent of C over T. And because we're going to be using Python later, Python doesn't let me use hyperbolic cotangent. It only lets us use hyperbolic tangent. So I'm just going to go ahead and write this as C over the hyperbolic tangent of C over T. And so that gives us this part. And then we also need the hyperbolic, well, the integral of this part here. And so I'm going to pull that over right here. and we see that it gives us, and it made this, the E, the capital E here, a lowercase e, so it's a constant that we'll be able to find later. And so this just gave us this equation that you see here. So I'm going to go ahead and copy this over into the notebook as well. So we've got negative E. No, that's not a hyperbolic tangent of E over T. All right. And so I'm just going to go ahead and plug in all of this equation so we have it for when we need it later on. So we've got A of T plus B times C over hyperbolic tangent of C over T. And then we've got this minus D times E to the hyperbolic tangent of E over T. And so we have that equation, and we're going to be able to use that later in Python, and it'll allow us to solve the problem. But first, what we need to talk about is the reaction going on, because we're going to have a mixture of this fuel, so we need to know how all of these fuels react with air. And so we're going to start out, and we have methane, and we're going to have that reacting with oxygen. But because this is air, not just pure oxygen, we're also going to have this nitrogen component. And so this is going to yield carbon dioxide and water. But also we are going to have the nitrogen, because the nitrogen doesn't react with anything in this situation. And so we're just going to go ahead and balance this out here. So we know that we are going to have 2 waters, and that is going to give us 4 oxygens, so we need 2 oxygens. But then the nitrogen, we know that it's air consists of 79% nitrogen. So what we're going to do is just set it up as a fraction, and we're going to need to multiply by the number of oxygens that we have here. And that will allow our stoichiometry to be correct. And so I don't want to keep writing that all out, so I'm going to go ahead and copy the important part here and go ahead and paste it. Ooh. And then I'm going to delete the parts we're changing. All right, so we're going to C2, H6, and then we now have 6 hydrogens, so we're going to need 3 over here, and that's going to give us this weird number here. So it's actually 7/4 number of oxygens, and we just kind of plug that in, and there's the balanced stoichiometry. And then just going to go ahead and paste it again and delete the unimportant parts. We're just deleting everything, it looks like. Alright, C3H8, and then that's an O2. And so we now have 8, so we need 4 down here, and then we have 3 here. And so I feel like I'm messing up the stoichiometry here. So we have 6, 10, so we have 5 oxygens here, and we just need to multiply by 5 on both of these ends. And so we have our balanced stoichiometry, we have our ChemCat equation for the integral here, and so now I'm going to jump over into Python, and we're going to go ahead and code out the situation and solve it really quickly. Alright, so now we're over in Python, and we're going to go ahead and code all this up. So you can see I already have some code in here. It's kind of just some basic things that we're going to need. This here this git clone is cloning a GitHub repository that has a bunch of chemcad stuff, and we were using chemcad equations, so we needed the chemcad data. And so that line imports the tools aspect, which allows us to see all of this. It allows us to get these properties of all the data. So if we pull up the methane here, it shows us all kinds of data on methane, and the important ones for us is going to be this heat of formation, and you can kind of see this right here. It's in kilomoles. We're going to have to keep that in mind when we're going ahead and coding this. We want to make sure it's in moles, not kilomoles. And then the other thing we're going to be needing is this ideal gas heat capacity, and these coefficients, those are our A, B, C, D, and E values. So those are also going to be important. So we're going to be needing to use this chemcad stuff here. And then I also needed to import SciPy root. We're going to use a root solver, and then NumPy, because we are going to be doing some math. So I'm going to go ahead and run both of these, and we can get to it. So the first thing we're going to need to do is get that property data. So we are going to get that from the GitHub site, and the way we're going to do that is using this CHE props. So this will get us our values. And so what values do we need? We need first of all methane. We also need ethane. And then we also need propane. And then the next one we need is oxygen. We're also going to need nitrogen. And then we also need carbon dioxide. And finally, we need water. So those are all the chemicals we need. Oh, I always forget to put the brackets. Always, always, always. All right, so that fixed our problem there. So the next thing we're going to need to do is figure out the number of hydrogens and carbons that we have. So we want the, what do I want to call it? We'll call it the fuel, carbons and hydrogens. Perfect. So we want to set that equal to, so we're just going to manually type these in because this is just the number of moles, or not the number of moles, the number of carbons and hydrogens in methane, ethane, and propane. So in methane we have 1 carbon and 4 hydrogens. In ethane we've got 2 carbons and 6 hydrogens. And in propane we've got 3 hydrogens. No, 3 carbons, 8 hydrogens. All right. Didn't mean to do that. And then, so the next thing we're going to need is the number of moles of fuel, of each of these fuels that we have. And so this is just going to be a value that we already have. It was given to us. We are going to make an array of this so that we're going to be able to do some matrix multiplication later. So it was given that we have 10 moles of methane, 1.5 moles of ethane, and 1 mole of propane. Alright, so now that we have that, we want to multiply them together to get us our total number of carbons and our total number of hydrogens. And so this we're going to set equal to the matrix multiplication of our fuel times matrix multiplied is at times our fuel of C underscore H. And what this will let us do is find out the number of moles of everything that we have. So the first thing we want to know is the number of, we'll start with carbon dioxide. So the number of moles of carbon dioxide is going to be equal to the number of moles of carbon. That one's pretty simple. Then we're also going to do the number of moles of water, and that is going to be equal to the number of moles of hydrogen divided by 2, and then we need the number of moles of oxygen, and that is going to be equal to the number of moles of carbon plus the number of moles of water divided by 2. We also need the number of moles of nitrogen, and that is going to be equal to the number of moles of oxygen times 79/21. And we get all of this from our stoichiometry over here that we've got over here. All right. So now what we're going to need to do is take all of this that we have and create some useful information. So we need to figure out how much we have going in and how much we have going out. So we want to figure out the total number of moles that we have going in, and we're going to do that by concatenating the number of moles of fuel that we have with the numpy array, with the array. Why does it keep doing that? With the number of moles of, so this part is these three here, our fuel, and then so we need the number of moles of oxygen to start with. So we've got number of moles of O2, and I am missing that darn bracket. I always forget that. And then we also need the number of moles of nitrogen, because we start with a number of moles of nitrogen. And then we are also going to need the number of moles of carbon dioxide and water. But since this is the amount going in, we don't have any carbon dioxide or water going in. So we can just kind of put those into 0 because we don't have any. And then we also need the number of moles going out total. So we're going to do something very similar to that. So we can just kind of grab this line and change it around a little bit. So because this is going out, we don't have any fuel going out. So what we're going to be able to do is actually use another numpy function, and it's called zeros like. And what this will do is create zeros in place of our fuel data. So if we were to go back in and change any of this, we wouldn't have to change the number of zeros we put in. It'll just automatically grab that for us. So this time we don't have any oxygen in here because there's no oxygen in our products, so that can go in as a 0. We still do have the nitrogen, and then we do have the number of moles of carbon dioxide and water. Got it. All right, so now that we have all that, what we can do is go ahead and start defining our functions. So the first function we're going to need is a function with our equation that we have over here that we created. Definitely need that. So I'm just going to call this the integral of the specific heat. And what this is going to take in as a variable is temperature. And so we're just going to go ahead and return. And then we want to return this whole equation over here. So we're going to go ahead and type that in. And like I was talking about before, the coefficients are going to come from the ChemCAD that we have in the repository. So we're going to need to call that. So we have to type in this big, long specific heat of ideal gas and then specify which variable we want to use. We're going to be typing that in a lot, so I'm just going to copy and paste it. So we need to multiply by the temperature and then plus the B value times the C value divided by the hyperbolic tangent of the C value divided by T. Let me just make sure we have all the parentheses here. Yeah, got all the parentheses we need. And then we're going to subtract by the D coefficient times the E coefficient times the hyperbolic sine, not sine, hyperbolic tangent of the E value divided by our temperature. And then let's just double check parentheses. And then you remember how we looked at the kilomoles. To convert to moles here, we need to divide all of this by 1,000. Perfect. And so the next function we are going to need is the function that'll give us the heat capacities, or the heat of formations. So we need the heat of formation of an ideal gas, and we need this to take in the number of moles and the temperature. And so we are going to return the dot products, the dot product of the number of moles and the heat of formation of an ideal gas plus the dot product of number of moles and the difference between our initial, or the integration of the heat capacities at the temperature T minus the integration of the heat capacities at temperature 298. And then we're going to need a third function, and this is kind of just setting up our root solver. And what should we call this one? We'll call it energy balance. We'll just shorten that to eval because, and we're calling it this because it's setting up this equation over here that we have in our notes, and this is just our energy balance equation. And this will just let us use a root solver. And we're throwing in the dummy variable T, or B here, so that we can just use T. It'll just make our lives simpler. And then we are going to return the heat of formation of an ideal gas. Heat of formation of an ideal gas. And we want the number of moles in and also the temperature. So we need to do that, and then we want to subtract from the heat of formation of an ideal gas with the number of moles going out, and then at the temperature 298. And so now we just need to use the root solver. And so we want to do the root of eval, energy balance equation. And we want to give it initial guess of, let's just say, 298 kelvins. And it gave us an error. I'm just going to go ahead and debug this, and I will come back to you once I get it solved. All right, I think I see it. I think I just need a period there. I think I just messed up and put a comma. That wasn't it. Oh, I see it. I was trying to call the function itself inside of its own function. We needed that to be the properties of the heat of formation. So we'll go ahead and rerun that through. It converged, but that value doesn't look right. It's negative. That is definitely not right. So I definitely messed up somewhere in here. So I'm going to go through and debug this again. I'm sorry. Oh, duh. I flipped my variables. There we go. So it's such simple mistakes make such big problems. I think it was just giving us the negative version of this value. So kind of an anticlimactic ending, but hope this teaches you not to make the simple mistakes that I've been making, and just make sure you're checking your work all the way through. Thank you for watching my video. I hope you enjoyed.